So this video is on the chapter 12, D-Day number 3. So for this, what we want to do is we want to, on the first one, try to get it so that maybe we can factor this, and then we can always want it to set equal to 0 if you're going to factor, and then see if we can factor and set those factors to 0. So on this number 1 here, I noticed that we have a sine x and a sine x. So I can factor sine x out of both terms, and we're going to be left with a 2 and a cosine x minus root 3 equal 0. The other thing you want to pay attention to here is they're saying for all. So this is going forwards and backwards on the unit circle forever and ever, because sine and cosine waves do continue forever and ever. We usually just graph one cycle of it, one period of it, but they do go on forever. So now at this point, what's going to happen is I have two factors. I set them to 0. So this one would be sine x equals 0. And we're going to work that out and see what x's would make my sine be 0. And then we have this one. And if I set that equal to 0, I am going to be adding my root 3 and then dividing by the 2. So that's what I'm looking at. So for the sine, my sine is your y, okay? So remember it is, I kind of color code this here. So when we're doing this on a unit circle, your x is your cosine, your sine is your y. So if I want my sine to be 0, I want my y to be 0. My y is 0 here because that point is 1, 0, but that's 0 radians. And here at -1, 0, which is pi. And these are pi away from each other. So what I'm going to do is I'm going to go 0 plus or minus pi n, because I can keep adding and subtracting pi to go around and around the unit circle. I really don't need the 0 in front. I could just clean this up to plus or minus pi n. I would accept either of those situations, okay? On the second part, the cosine is your y, is your x. And so when we're doing this, we want to think about, well, where would my cosine be a root 3 halves? So when I think about these, I think about the following. 1/2 I consider short. Root 2 halves would be the one in the middle, okay? And that would be at your pi force. And your root 3 halves is your long. So where people have trouble is with the following 2 points. 1/2 comma root 3 halves and root 3 halves comma 1/2. Which one's which? So every time I want a 1/2, I think short. Every time I want a root 3 halves, I think long, okay? So if I want my cosine to be root 3 halves, I want it to be long. So I'm going to be going out long, short. I'm going to be here. And that is at pi 6. Now, cosine is also positive in quadrant 4. So I'm also going to be here. And that going around my unit circle, all the way around, is going to be at 11 pi 6. Now, when you're doing this, you want to kind of pay attention to whether or not you can get back and forth between them by adding or subtracting one thing. Like I could from 0 to pi, it's the same distance this way as it is this way, okay? But if I'm going from pi 6, whoops, still on the eraser, sorry. If I'm going from pi 6 all the way around to here, hopefully you can see that that's not the same as the distance from here to here. Okay, so I can't just add something on to pi 6 and get my 11 pi 6. So I'm going to have 2 answers here. Okay, and here, let me clean up this down here so I can write my answer here. Okay, so I am going to have also as my answer pi 6 plus or minus 2 pi n, because if I add 2 pi, I'll end up back at that same location, okay, whether it doesn't matter which direction I go, and at 11 pi 6, again, plus or minus 2 pi n. And these are my answers. Again, you can either write it with the 0 plus or minus pi n or just plus or minus pi n for the first one. Okay, on number 2. This time they're giving us an interval. They want us to go from 0 to 2 pi. So I'm going to start here. I'm looking all the way here to here, but I'm not going to include 2 pi. That's why it's an open bracket. Okay, so that's what I'm looking at. Okay, so this is just has a sine squared. I'm going to isolate my sine squared. So I'm going to add 1. I'm going to divide by 2. I'm going to take the square root. Now, when I take the square root, I get a positive and a negative. So sine and cosine and tangent and all the other trig functions, we have 2 positive quadrants for each of them and 2 negative quadrants. So since I have a plus and a minus, I should be getting 4 answers for this. And when I take the square root of a fraction, I take the square root of the numerator, which would still be 1, and the square root of the denominator, which would be a root 2. Now, we may not recognize this on the unit circle because we like to have it in rationalized form, where I am multiplying top and bottom by root 2, and I want to know where my sign is equal to positive and negative root 2 over 2. That's at all your pi fourths, okay? So I'm going to have here at pi fourths, that would be a positive root 2 halves for my, that point is root 2 halves comma root 2 halves. So all of the x and y's for my pi fourths are root 2 halves, but the sign might change. This over here would be 3 pi fourths. This over here would be 5 pi fourths. And this over here would be 7 pi fourths. Now, in this case, I want 0 to 2 pi. So these 4 would be my answers. I would have x is equal to pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. If this was a problem where they had said for all and did not want just one time around the unit circle, what you can see is the distance from here to here, from pi fourths to 3 pi fourths is 2 pi fourths. This is 2 pi fourths. This is 2 pi fourths. This is, again, 2 pi fourths. So if I was doing a for all, which I'm not, but if I was, since every single thing is 2 pi fourths or pi halves away, I could have, I'll do this in light blue, here temporarily, I could have done pi fourths, and then again, I'm adding 2 pi fourths, which is just pi halves n. And that would have taken me around and around and around the circle. That's if they had said for all, okay? Okay, on number 3, this one does say for all. So we need to pay attention to that. Okay, so they want for all x. So this one, I've got a sine squared, a sine x, and a 1. Getting that 1 to the other side is not going to help because I have a sine squared and a sine x. I'm going to have to factor this. I want it equal to 0 like it is. So this one, if you want to do box to diamond, you can. I'm going to be focusing on this. I'm going to be focusing on the front. I need to get a 2 sine x. So that would be a 2 sine x and a sine x. And then I'm going to be focusing on the back, which is a positive 1. Now, that could be a 1 and a 1 or a negative 1 and a negative 1. But because this is positive, it's going to be a positive 1 and a positive 1. So those are my factors. And you'll see that would have given me a 2 sine x. This would have given me a 1 sine x, which gets that 3 sine x that I needed. Okay, so now I'm going to set each of these to 0. So if I set this one to 0, I get 2 sine x equals a negative 1. I get sine x equals a negative 1/2. If I set this one to 0, I get sine x is equal to negative 1. So Sine x is equal to -1/2. Again, sine is your y, 1/2 is short. So, and it's a negative sign. So negative sign is going to be down in the bottom quadrants, 3 and 4. So I'm looking at long comma short, which would be here, and long comma short, which would be here. So that is pi6. So this would be 7 pi6 and 11 pi6. And you can see that the distance between these is not the same in both directions. The distance from here to here is a lot shorter than here to here. So I'm going to have to write them out separately. Okay, I can't write one in terms of the other. So for this, it's going to be 7 pi 6 plus or minus 2 pi n and 11 pi 6 plus or minus 2 pi n. So those are the answers that would get the first parenthesis to 0. The second parenthesis is sine x equals -1. And again, sine is your y. I want to know where my y is -1, which is down here at 3 pi halves. So this is going to be 3 pi halves plus or minus 2 pi n. So those are your answers. On number 4, we're going to be verifying. So I want to try to get the left-hand side to equal this right-hand side. Okay, so I'm going to keep the right-hand side and I'm going to work on the left-hand side. So I noticed that these are, that I have a sine squared on the other side. So there's a couple of ways I can think about doing this problem. So you could rewrite your secant squared x's as 1 over cosine squared x's. That's one way to do it. Another way to do it is to recognize this right here. Let me highlight it in purple. Recognize that. That comes from our Pythagorean identity, where we have 1 plus tangent squared x equals secant squared x. So if I have tangent squared x, that is going to equal secant squared x minus 1. So I think I'm going to go that route, and I'm going to put tangent squared x here. And then on bottom, I still have my secant squared x equals sine squared x. Now I'm going to rewrite my tangent squared x and my secant squared x in terms of what they are. So just a little reminder here. Let me just, again, color code here. Tangent squared x would be sine squared x over cosine squared x. And my secant squared x is 1 over cosine squared x. Okay, so I'm just writing these out so you know where I'm getting these things from. So tangent squared x is going to be, and here, let me rewrite that. So that's going to go here. And so that's going to give me a sine squared x over cosine squared x over 1 over cosine squared x. And then if I clean that up, I can rewrite this as sine squared x over cosine squared x. When I divide by a fraction, I can multiply by the reciprocal. And now you see that these cosine squared x's will cancel out. And I am ending up with my left-hand side being a sine squared x. And remember, my right-hand side was supposed to be stay a sine squared x, and I got my answer. On number 5, so if I have a 2 sine A, okay, this is one of those double angle formulas, and 2 sine A, there's only one formula for this, and it's 2 times sine of A cosine A. So what I'm going to do is, this is in quadrant 3, they said. So if I draw a triangle in quadrant 3 and have this be A, my sine, which they gave us here, right here, is -3/7, and sine is opposite over hypotenuse. If you look and see, my y direction has to be negative because I'm in the negative y quadrant. My hypotenuse will never be negative. Okay, it's always going to be a positive. And if I do Pythagorean, I'm going to get, to find the x value here, I'm going to be doing x squared plus a -3 squared equals 7 squared. So I'm going to get x squared equals basically 49. I have a 9 on the other side. I'm going to subtract it. So I have x squared equals 40. So that's going to be the square root of 40. And I can clean up the square root of 40. There is a perfect square in there. It's a root 4 times a root 10. Root 10 that does not have any squares in it. So that's a 2 root 10. So this x over here is really going to be a negative, because of where I am, I'm in the negative x direction, 2 root 10. So now that I know that my x is a -2 root 10, I can put that into our equation. 2 times, and our sine of A is -3/7. So that was given to us, but also we'd see in our picture. And our cosine of A is going to be a -2 root 10/7. And so when we do that math, I am going to have 2 times -3 is -6, times a -2 is 12. 12 root 10/49, and that is our answer. Now on number 6, this is one of those double angle formulas. A lot of the ones we had seen were where we had the sine and then the cosine. This one I have cosine, cosine, sine, sine. So this is one of the cosine ones. And so this is going to be cosine of, basically, if this is a plus, then I'm going to have a minus here. So this would be A minus B is equal to cosine of A cosine of B plus sine of A sine of B. This is a formula I'm looking at. And we want to write this as one trig function of one angle. So I don't want cosines and sines. I want one, and that's going to be a cosine, and that's a minus there. It's going to be a cosine, and I'm going to take the two angles and I'm going to subtract them. So I'm going to have cosine of, one sec, cosine of 5 pi eighths minus 3 pi eighths, which is cosine of 2 pi eighths, which is cosine of pi fourths. Now they asked us to write it as a single trig function of a single angle, but we actually could compute that because we do know what cosine of pi fourths is. That is equal to root 2 over 2. Okay, so that's what that equals. They did ask us to write it as one trig function of one angle, so that's what that answer is. But again, they could have asked us to evaluate it, and we would have changed it to this form and then realized that cosine of pi fourths is root 2 over 2. On number 7, so this is review from last chapter, and we need to get a common denominator. So I am going to multiply top and bottom to end up getting an x minus 2 times an x plus 1 as a common denominator. So over here on this side, I am needing to multiply top and bottom by an x plus 1. So that would give me a 9x plus 9 over x minus 2 times x plus 1. And on the other side, I do have a minus, so I want to make sure I have my negative. And I'm going to multiply top and bottom by x minus 2. And so when I am multiplying x plus 2 times x minus 2, that actually is a difference of 2 squares, which is an x squared minus 4. But I have a minus that's going to distribute. So now I am going to clean this up. So I'm going to have a negative x squared plus a 9x. And then here, this negative times negative, let me do it in a different color here. That's not with the shape, not what I wanted. This negative times negative is going to end up being a positive. Okay, so that's going to give me a positive 4 and a positive 9 is a positive 13. And that is going to be over x minus 2 times x plus 1. We can try to factor it, but nothing multiplies to 13 and adds to a 9. And I do have a negative in front also, which isn't helpful. There you go. That's your answer. On number 8. Okay, so on this one, this is a reminder of the binomial expansion, okay? And so for this, if I want the fourth term of this, I am going to take this. I'm going to go 5 minus 4. And so I'm going to take the power that I'm raising the binomial to minus the term I want plus 1, always plus 1. And that is going to give me 2. So then I'm going to take the 5, which is the power raising the binomial to, choose 2, this 2 that I just found, times my 3x to the 7th raised to the power 2 times my negative 4, and then 5 minus 2 is 3, so that's going to be a 3. I'm going to then put that into my calculator and get my answer, okay? So 5 choose 2 is 10. Here, everything in that parenthesis, my 3 is being raised to the power 2, which is a 9. My x to the 7th is being raised to the power 2, and power to power, I multiply. And then I have a negative 4 to the power 3, which is a negative 64. And then when I take 10 times 9 times a negative 64, I end up with a negative 5,760 x to the 14th, and that would be our fourth term. So this problem is from our last chapter also. We're going to be setting up a system of equations. I am going to be taking 1, 3, substituting it in. So I'm going to get 3 is equal to a times 1 squared plus b times 1 plus c, which I can clean up to 3 is equal to 1a plus 1b plus c. And then I'm going to be putting in 2, 2. And I'm going to get 2 is equal to a times 2 squared plus b times 2 plus c, which is 2 is equal to 4a plus 2b plus c. And then I'm going to be trying to do 3, negative 3. I'm going to get negative 3 is equal to a times 3 squared plus b times 3 plus c, which is negative 3 is equal to 9a plus 3b plus c. And my goal is to try to eliminate one of the variables and get 2 equations and 2 variables. C would be the easiest because each of them has just a plain C. So I'm going to multiply the top one by negative 1. And I'm going to end up with negative 3 is equal to negative a minus b minus c. And I'm going to do it with the orange one first. So that is going to be 2 is equal to 4a plus 2b plus c. And adding these together, I get -1 is equal to 3a plus b. I'm going to take that same pink equation I multiplied by -1, which is -3 is equal to -a minus b minus c. And I am going to use it with my purple equation. So that is going to be -3 is equal to 9a plus 3b plus c. I'm going to add these together. And I'm going to get -6. -6 is equal to 8a plus 2b. Now I can divide this by by 2. And if I divide by 2, I'm going to get a 1 here. And here is a 1. But I think instead I'm going to divide it by a -2 so I can get a -1 there. So I'm going to divide by -2 by -2 by -2. And when I divide by -2, I'm going to get 3 is equal to -4a minus b. And so now I'm going to take these two equations. So I'm going to take my blue equation, which is -1 equals 3a plus b. And the one I just wrote in black, 3 is equal to, let's see, -4a minus b. I'm going to add these together. And I end up getting -2 is equal to -a. And that means that 2 is equal to a. And let's see. Oh, sorry, this is a +2. I apologize. This is a +2 is equal to -a. So a is going to be a -2. Okay, -2. Doing some bad math there. Okay, so this here gives me a +2. So that means my a is going to end up being a -2. So that's my a. So now I'm going to take that and substitute that into, I'm going to do it into my blue equation. Okay, because I'm going to do it into one or the other of these two that have just a's and b's. So I'm going to go -1 is equal to 3 times -2 plus b. -1 is equal to -6 plus b. So I'm going to add 6 and I'm going to get 5 is equal to b. So I have my a and my b. I'm going to come up to either the pink, the orange, or the purple equations. I think I'm going to do it in the pink equation. I think that'll be the easiest math. So let's see. I'm going to have 3 is equal to 1 times -2 plus 1 times 5 plus c, which is going to give me 3 is equal to -2 plus 5 plus c. So I'm going to get 3 is equal to 3 plus c, which means c is 0. So my equation is going to be, because that's what we're trying to find, was an equation of a parabola. My equation is going to be y equals -2x squared plus 5x plus 0, but I don't need the plus 0. That's your equation. Okay, similar process on the next one. It is a system of equations. We want to try to get 2 equations with 2 variables and then solve. So looking at this one, I actually have an equation. Let me highlight it. This equation right here, that is 2 variables, has an x and a y. So I'm going to keep that equation. Okay, and here, let me just kind of number these. Let's say I call this one number 1, number 2, number 3. So I'm going to keep equation 2. So that means I'm going to use equation 1 and 3 and try to eliminate my z, since that other equation doesn't have a z. That's probably the easiest way to go about doing this. So I am going to multiply the top equation, equation 1, by, let's say a -5. And I'm going to multiply the bottom equation, let's say, by a 3. So I get a -15z and a +15z. Okay. So I'm going to get -5x plus 10y minus 15z is equal to a -45. And I am going to get 6x minus 15y plus 15z is equal to, when I take 17 times 3, I'm going to get 51. So I'm going to add these together. And when I do, I am going to end up with x minus 5y, my z's cancel out, is equal to 6. So I'm going to take that equation and equation 2, and I'm going to solve that system. So let me write equation 2 out as -x plus 3y equals -4. Let me take my equation I just got, which is x minus 5y equals 6. And you can see that I got a system of equations with 2 variables. And the nice thing is when I add these, my x's are going to cancel out, and I get -2y is equal to 2. So y is going to be -1. So now I'm not quite done. I need to still finish solving the system. I think I'm going to put it into the purple equation here to find my x. So I'm going to go x minus 5 times -1 equals 6. X plus 5 equals 6. So x is going to equal 1. And then I have to put it into either equation 1 or 3 because the other one doesn't have a z. So I'm thinking equation 1. Okay, so I'm going to put it into my equation 1. So let's say I have, in place of x, sorry. So it's going to be x, so it's going to be 1 minus 2 times -1 plus 3z equals 9. So 1 plus 2 plus 3z equals 9. So 3 plus 3z equals 9. I'm going to subtract 3 from both sides. So I get 3z is equal to 6. So z is equal to 2. So my final answer is going to be 1, -1, 2. That is my solution. And that's the end of this video.